Geometry, Section 11.6, Geometric Probability. By the end of this lesson, you should be able to calculate geometric probability. Before we can talk about geometric probability, we need to talk about what probability is. And probability is a number between 0 and 1 that represents the chance that an event will occur. So we might hear this in sports. So somebody might have a shooting average, and we end up saying that there's a 40% chance that somebody would make their free throw shots. We can also see this in the classroom. So if we were to count up all the boys and girls and the total students in the class, you can determine the probability that at random a girl would be selected to answer a question. All of this is probability. Now it is a number between 0 and 1, which can be kind of confusing because we usually think about this as percents. Now, assuming that all outcomes are equally likely to occur, an event with probability of 0 cannot occur. So if there's a 0% chance of something happening, it'll never happen. An event with a probability of 1 is certain to occur. Now this is because probability can be written as a fraction, percent, or decimal. So we're very familiar with the percent, but we need to be familiar with it as a fraction or a decimal. So if we were talking about there are 4 girls in a class of 10, which can be simplified to a 2/5 chance of a girl being called at random, or we can also put this in decimal form and say this is a 0.4 chance, or we can translate this into a percent and say this is a 40% chance of this occurring. So any of these are all acceptable ways to represent probability, but you need to be familiar with all of them. Geometric probability is relating this to geometry. So we have 2 scenarios that we're going to be focusing on, and one of them is if we're talking about length. So if we have some segment AB and it has another segment contained in it, CD, and I wanted to find out what is the probability that if a point was picked at random, that it would lie on CD. And to be able to do that, this all stems from probability being your number of desired over your total. So the desired segment or points would be contained within CD. In other words, that's also the length of segment CD. Now the total would be the length of segment AB. If you get these 2 measures, you can calculate the probability of point K, or any point being picked at random, being on this segment CD. Likewise with area, you might have a desired portion. We see this with darts and even with some of the activities we did in class. But if we have some region J, which would be our total region, and it has this other region M, then if you were to draw a point at random, or throw a dart, or toss a beanbag, then the probability that it would hit this figure M would be calculated by finding the area of M and dividing that by the area of J. And that would give you your probability. Let's try a few examples. So here we have find the probability that a point chosen at random on PQ is on RS. Well, first I need to take a look at PQ, and that's this entire segment. Let's get the highlighter out for this. So we have PQ, and we also have RS, which is this segment here, and we want that probability. So probability always stems from your desired over your total. And in this case, we need to make sure that we're taking our desired length of the segment over the total length of our entire segment. Now, RS, to figure out RS, I know that it has a point, an endpoint at 7 and an endpoint at 13. So we can say 13 minus 7 will give us the length of RS, which will become 6. And the total length is going to be 20, which is simple because we're just getting that from 20 minus 0. And this is all coming from, remember, we're finding out the length of RS over the length of PQ. This simplified, we end up with, you can say 3/10, or you can represent it as a decimal, which would be the same thing as 0.3, or you can represent it as percent, which would be a 30% chance. So all of these would be appropriate answers, but you don't need to write all of them. Next, we have one that deals with area. So find the probability that a randomly chosen point in the figure lies within the shaded region. Now this one's interesting because our shaded region isn't this giant circle. Our shaded region is this portion outside of the circle but still within the trapezoid. So we need to calculate our desired over our total. Now the entire figure is our trapezoid. So if we were to calculate the area of the trapezoid, that would be our total. Now our desired is our area of our trapezoid, but I need to take out this portion that's occupied by the circle, so I'll have to subtract the area of the circle. So to do this, I'm going to make two little mini problems, and I'm going to need to calculate the area of the trapezoid. So the area of the trapezoid, remembering our formulas from area for trapezoids, would be calculated by base 1 plus base 2 divided by 2, and all of this times our height. So to calculate our area, we would have our base 1, which is 18, plus our base 2, which is 25, divided by 2 times our height of our trapezoid, the distance between the two bases, which is 20. This will work itself out to become 430 units squared. Next, we need to calculate the area of the circle. This one's a newer formula, and we should know this. That is found by pi times radius squared. And so our area is going to be pi times, well, we need to figure out our radius. Looking at this, I know that this circle appears to be tangent with the two bases. And if that distance between those two bases is 20, that means our diameter equals 20. So half our diameter is our radius, and we can say that our radius is 10 units. So we'll say pi times 10 squared. This will become 100 pi units squared. So now that we have these two pieces, we can go ahead and substitute them back into our original probability ratio, or fraction rather. So just kind of blocking this all off to the side, we have our area of our trapezoid, which was 430 units squared, minus the area of our circle, which was 100 pi, divided by the area of the trapezoid, which is our total. So that's 430 units. So we can calculate this. And to do so, we need to make sure we use our parentheses. So we'll say, let me clear this out, 430 minus 100 pi, and the parentheses for 100 pi, and it again for the numerator, and divided by 430. For this, we get 0.269. So what this means is that there is about a 27% chance of randomly choosing a point that's in this shaded region. That's all the practice for today, and we'll do some more in class. So it's time for our joke. What do you call a fake noodle? Well, you call it an impasta.